All right, so in the last video, we saw that there are some trends in the bond angle, right? And particularly as we went down the periodic table, we got a greater preference for being pyramidal. That led to a smaller bond angle. This also led to a larger inversion barrier, which gave some interesting ramifications for chirality, right? So why is this bond angle trend true? Why is SH3 plus have a smaller bond angle than hydronium? And why does arsine have a smaller one than phosphine than ammonia? So just like we did when we were considering bond angles in periodic trends for the linear to bent cases, it's the same idea here. Here I've couched it in terms of electronegativity. Before we couched it in terms of ionization potential. But as the central atom becomes more electronegative, MOs with more central atom character will decrease in energy the most. Another way of saying this is, as you go down the periodic table, your ionization energy is going to go up. Those are going to increase the most, right? Electronegativity goes down as you go down the periodic table. So I've been thinking about this time in terms of electronegativity. So drops the most. All of them are going to drop down with increasing electronegativity, but the ones with the most central atom character are going to drop the most because those are most affected. They have the most central atom character. So if you change the central atom, those are going to change the most, right? So the non-bonding ones, or the ones that have most electron density on the central atom, those are going to change the most. So that's going to be, this one's the only one that's strictly non-bonding, right? This one actually has a little bit of bonding after mixing. So this orbital is going to become really important. This is going to drop down the most. And so this tells you that the planar case is going to be stabilized, right? If this goes down more, that's going to be stabilized with increased electronegativity. Well, what's increased electronegativity? That's higher on the periodic table. So that is consistent, right? Higher on the periodic table, planar stabilized. Ammonia has a bigger bond angle, closer to planar. Still pyramidal, right? But more preference for being planar, ammonia does, and so does water. The oxygen and nitrogen are more electronegative than sulfur or phosphorus, right? And then the second thing that is going to change is size, right? And we talked about when you have more size, you're going to, bigger size, you're going to have bigger orbitals that have more diffuse character. More diffuse character means less localized electron density, means weaker bonds. So all of your bonding interactions are going to get weaker. That's going to raise them in energy. All your anti-bonding interactions are going to get weaker. That's going to decrease them in energy because anti-bonding are unfavorable interactions, right? But notably, look what happens here. You had these ones that mixed, right? And so before they mixed, right, now they're going to be closer in energy because this bonding one's going to go up, this anti-bonding one's going to go down, and that's going to cause them to drive apart and mix even more. And so as a result, this HOMO here for pyramidal is going to go down with larger size. And that means that pyramidal is stabilized with increased size. And that's exactly what we also see, right? The arsenic containing compound, arsine, has the biggest size and has the smallest bond angle, most stabilized for pyramidal. Sulfur one has a bigger size than hydronium with oxygen, so most stabilized for pyramidal, smaller bond angle. So all those things are consistent. So I think what's really neat about this chapter is we finally have gotten away from VSEPR. We have a theory in its totality that we can use to justify and predict accurately using quantum mechanics all of many different structural properties of molecules, including bond angles. VSEPR tried to do these things, but there was a lot of after-the-fact rationalization. There was a lot of times when VSEPR got it wrong and we had no explanation for it. And this is a theory that is based on quantum mechanics, and it's not a standalone empirical-based theory like VSEPR. All right, guys, so that's it for chapter 6. I'll happy to answer any questions that you may have in class, so please keep coming to class, and I'll see you on chapter 7 next time.